Okay. And we are going, I think. Oh, wait, hold on. This is C. C. Combining functions and composite functions. Okay. So let's begin. So this particular section of the textbook, this is 5.3. I'm breaking this into two parts. So this part is just focusing on the theory of combining functions into new functions, and then the next part, lesson 2D, is going to be doing it algebraically. Because, how should I put it? The algebraic procedures are very important. It's very important how to know how to do the algebra, but why we're doing the algebra in that way and different themes will show up just based on the basic theory. So I've split this into two. We're going to talk about basic theory first, and then we're going to move into algebra. Okay, so at the end of this, you should be able to use, if you're given a table or arrow diagram for a function f and a function g, you should be able to make a new table or arrow diagram for f plus g, and another function called f minus g, and another function called f times g, and another function called f divided by g. We're going to go through each of these. You don't need to do them all at once. Then I want you to evaluate a combined function, which is the previous ones, f plus g and all those, for a given input. So how do we evaluate one of these combined functions? It's not tricky. Then I want you to talk about the domain and the range of the new combined function. There are subtle things at play here, but they're not that subtle. You can pick them up. They're pretty straightforward. And then we're going to talk about something called composite functions, which is a different way to stick two functions together other than adding or multiplying or dividing. And so given a table diagram or a table or an arrow diagram for functions f and functions g, I want you to be able to make a new table or arrow diagram for f of g. And then I want you to be able to evaluate it, which those two go hand in hand. We'll talk about these as we get to them. They're not that complicated. Okay. So sometimes you get two functions. Sometimes you get two functions. How's that, huh? F function and a g function, and you want to combine them to make a new function. Why would you do that? Well, let's take a second here and imagine I have a coat factory. Okay, so I've got two employees, Frank and Greta, and they each make coats. And so how it works is I go in and I say, hey everybody, we're going to work for X hours today. And then each of these employees works for that number of hours, and based on their records, here's how many coats I can expect them to make. So Frank's coat function looks like this. If I give him 1 hour, he'll make 1 coat. If I give him 4 hours, he'll make 5 coats. If I give him 5 hours, he'll make 8 coats, right? And Greta's function reads a similar way. If I give her 2 hours, she'll make 1 coat. If I give her 4 hours, she'll make 4 coats. If I give her 5 hours, she'll make 9 coats. She has a very interesting way of making coats that involves, I don't know, putting stuff aside, mass producing them. Anyway, so each of these people have a function describing how they make coats over a specific, given a specific time interval. But I don't care about them individually. All I care about is how many coats my factory makes at the end of the day. Okay? So if I give them 2 hours to make coats, So if x is equal to 2 hours, then Frank will make 2 coats, and Greta will make 1 coat, and I will have a total of 3 coats. If instead of 2 hours I give them, 5 hours, Frank will make 8 coats, and Greta will make 9 coats, and I'll have made 17 coats. You see? So sometimes, so I don't care about how many each individually make. I care about how many the overall team makes. And so for that reason, it's not helpful for me to add this together as a last step every day. I want to make a new function that describes how many coats my factory makes. And the number of coats my factory make will in time x is found by adding the 2 functions together. So I get a new function. I'll call it f plus g, which means that I add the 2 together. 2, 3, 4, 5. And then I can just calculate how many coats I'll have. So if I give them 1 hour, Frank will make 1, Greta make 0. So that's, the output is 1 coat. If I give them 2 hours, Frank will make 2 and Greta will make 1. So total is 3. 3 hours, 4 plus 1 is 5. 4 hours is 9. 5 hours, 17. And now that I have this table, I can just look it up to tell how many coats my factory will make. I built this new function by combining the 2 previous ones. So let me emphasize here. Okay, this table here is a function. This table, though, is built by combining 2 other functions together. You see? I combine 2 tables to make 1 table. I combine 2 functions to make 1 function. And that's the basic of combining functions. Essentially, given 2, I can produce 1. So let's try a similar exercise with arrow diagrams, right? Because drawing a function just with a table is one way of doing it. Arrow diagrams are a different way. So I want to figure out what the arrow diagram for the function f plus g is. So f, I guess, is the number of coats that Frank makes. G is the number of coats that Greta makes, or whatever. And f plus g is the factory total, if you want to think of it that way. How do I figure out the answer to it? Well, what I have to do is evaluate this function and this function for each of the inputs they have in common. Okay? I'll get to that later. So when the input is 1 hour, I guess, Frank is 2. When it's 1, that's 2. So overall, when the input is 1, the output's going to be 2 plus 2, 4. You see? All right, let's try it for a different one. When x is 2, function's equal to 3, and this one's equal to 1. So 3 plus 1 is also equal to 4. Why don't you pause the video and try filling in the rest of this diagram and see if you get it right. All right, so let's continue on. 3 goes to 5, so f is 5. 3 goes to 4, so 5 plus 4 is equal to 9. So when the input's 3, the output's going to be 9. Change colors here, it's getting confusing. 4, the output's 5. 4, the output's 3. So 3 plus 5 is 8. So when the input's equal to 4, the output's equal to 8. Well, 8's not on here. Better write 8. Yep. And the last one, when the input's equal to 5, the output's 6, and the input's 5, the output's 5. So 5 plus 6 is 11, and the output is 11. So the result of combining 2 functions like this is a whole new function, a whole new arrow diagram. But this arrow diagram was built using these two arrow diagrams to start with. Does that make sense? Let's try evaluating one of these before we go any further. Okay. So somebody might ask you, hey, evaluate f plus g, so that's the name of the function, at x is equal to 2. Now before, you could do this by evaluating f at 2, that's 3, and evaluating g at 2, that's 1, and adding them together, so it's 3 plus 1 is 4. But now that you have this new diagram, you could just refer to this new diagram, set that equal to 4. Does that make sense? Okay, so this is a little bit convoluted, but think about it as a game. Essentially, that's all it is. It's a game called take these two original functions, take the recipe that we're combining them, and draw your new pickle diagram. Okay, so the thing is, everything we talked about, that's for addition. You can also combine functions using subtraction. And each time I introduce one of these, I'm going to introduce with a little word problem kind of application, because sometimes it's pretty helpful to think about these things in terms of applications. We're not doing anything more than subtracting or adding terms, but the reason why we're doing it, it's helpful if you want to keep track of what's going on. So, Farmer Bob has tomatoes in his garden. If x is the month, f of x is the total number of tomatoes grown to date. Which is fine, except that he has a dog. His dog is named Ginger. Ginger eats tomatoes. And so g of x represents the number per month, in terms of the month, it's the number of tomatoes eaten to date. Okay? And so we want to know how many tomatoes the farmer has at that month. How many tomatoes does the farmer currently have at month X? Okay. So obviously this is a subtraction issue, right? I mean, in month 1, the farmer grows 20 tomatoes and the dog eats 10. And so at the end of month 1, he only has 10 tomatoes. At the end of the second month, by the end of the second month, over the year, the farmer has grown 30 tomatoes, but the dog loves these tomatoes. There's none. 50 minus 10 is 10. 60 minus 50 is 10. 80 minus 55 is 25. And so what we end up with is a new function which describes how many tomatoes the farmer currently has in month X. But I built this table, this function, out of these two. I combined them together to get this new function. I've built a new function out of simpler functions. Okay? We can also do this with multiplication. So how about a multiplication? I thought I put these farther apart on the table. I wrote all the function tables out to save some time in advance. So you might want to be pausing and saving it, but like I don't know. I thought we were pretty good for the amount of space we had. We're running out of space. Let me get some more space here. Okay, so We are measuring ice. Ice formation on a lake. It's winter, and because of the lake, what it does is it freezes. Here's the lake, and a big chunk of ice will freeze in a rectangular shape. Why? Because I said so. So the length this way in terms of x, is the hour since we started measuring. This height of the length of the ice on the western side is f of x. So I have a grad student out there with a measuring tape measuring how long that line is. I have another graduate student over here measuring how long this side is, along the northern side, right? And then I'm going to take those two pieces of data and I'm going to combine them to find the area. Because the area is just going to be G times F. So my grad students helpfully went out and they measured everything, and then they presented their data to me. Instead of a useful table, they presented it in an arrow diagram, where this is the hour, and this is the length of ice. So I'm going to have to be a little bit interprety as I figure out what the area is in terms of the hour. It's not that tricky, though. It's all about multiplication. At hour 1, the length is 1 on this direction, and it's 2 in this direction. So the overall length here is going to be 1 times 2. It's 2. Okay? So at hour 1, the area is 2. At hour 2, the length is 1, and this length is 1. 1 times 1 is 1. Weird. Hour 3. 3 length is 2. Hour 3 length is 2. So now the area is 4. Hour 4. This length is 2, and this length is 4. So the overall area is 8. In hour 5, this length is 3, this length is 4, so the overall area is 12. There. So this function describes how much area there is on my of ice as a function of what hour it is. Does that make sense? I figured out what this function was given these other functions describing the data that my friends measured. So you can add functions to make a new function. You can subtract functions to make a new function. You can even divide. All right, so Aaron is writing a test. Is at school writing test. So every month, she writes a few tests, and she gets each of these tests back, and she adds their scores to the pile. Each of them is scored out of 100, so it's their percentage, right? 70, right? And so she adds them up to figure out what the total is. 120. Okay. So she'll have written a certain number of tests up to date, and she adds them together to figure out what her total is. Total score. That's not the average score. That's like the total score, right? So if she got 50% and then 50% and 50% in her first 3 tests, her total would be 150. Okay. So she makes functions representing how many, what the total her test is, maybe total of scores, to date. And she also makes another function representing how many tests she's written. So her cumulative average to date is going to be her total score, her total of all the scores divided by the number of tests she's written. So let's make a new function representing what the total of her class is, her cumulative average over a course of time. So in month 1, she's written 1 test, and her cumulative score is 70. 70 divided by 1, so that's 70%. Good. Month 2, her total is 240, and she wrote 3 tests in there, so overall, so it's 80. Month 3 looks like she wrote 3 more tests, 2 more tests, so the total test she's written is 5, and her cumulative score is 300. Uh-oh. Looks like her average has slipped. Month 4, it's 420 divided by 7, which is 60. Month 5, 700 divided by 10. Oh, and her average goes back up. So just like before, I've made a new function built by combining these old other functions. Okay. So you can do it with adding, multiplying, dividing, subtracting, whatever you want to do. Okay. So before I go on, I want to make a note here about domains and ranges. Remember, the domain is the collection of all inputs with a defined output. And the range is the collection of all outputs. So the range will kind of deal with itself. You just kind of calculate that. What I want to focus on right now is the domain. Okay? In other words, when I'm making this table, what entries should I put in for x here? That's the question. So what you do is you just kind of look at it one at a time. So you go, okay, well, how about x equals 1? X is in this domain. X is in this domain. So the answer is fine. It's 2 plus 1 is equal to 3. 2. Is that in? That's in this one. Is it in this one? Yeah. So it's going to be 1 plus 3 equals 4. 3. That's in this one. 3 isn't in the domain of g of x. In other words, if I wanted to calculate it, it would be 6 plus does not exist. So the answer is does not exist. And if I wanted to, I wouldn't even have to write 3 on the domain of here. Okay, 4, yeah, that's in the domain. 7 plus 7 is 14. 5, it's minus 1 plus does not exist. And so, and then for 6, it is and does not exist plus 4. Okay. So long story short, x is in domain of f plus g, or f times g, or x minus g, or whatever, as if it is in both domains of f and the domain of g. Okay? So if one particular number, say like 3, is not in one of these domains, then it means that it's also not in the domain of this one. Okay, so that this is true for f plus g, it's true for f minus g, it's true for f times g, and it's true for f divided by g. But F divided by G has an additional issue. Why don't I just compute these for fun? Look, their domains are the same in both these cases. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. I shouldn't have any problem with these. Let's calculate these. So it's 0.333 on my calculator, and this is 0.25 on my calculator, and this is 0 on my calculator, and this one is T and E. And this one is -2 or -2 as 1 on my calculator. This is the one I wanted to point out. X equals 4 isn't in the domain. Because the output isn't defined. Why isn't it in the domain? It was in the domain of both of these. Right? Those are both defined. The issue here isn't that the individual functions don't have outputs that are defined for x equals 4. It's that g of x, g of 4, is equal to 0. That's the problem. You're not allowed to divide a number by 0. When you divide, when finding the domain of f divided by g, you need to exclude any numbers where g gives you 0. Okay. So that's a big issue. But essentially, when you're calculating domain and range, especially in these terms, you just make a new table and then you write the DNEs, and then if you want to, you can remove them afterwards and say, oh, in this case, the domain of this expression is f divided by g is 1, 2, 3, 5. 4 is not in it because g is equal to 0 there. So I'm going to ask you about these. This is an issue that comes up a little bit later and quite often, and so you got to be careful with it. Okay. So, on to the next part. Let me clear some room here. I'm going to teach you there is another way, a fifth way of combining functions that isn't addition, subtraction, and division. It's called composition. Composite functions. So let's say you're a farmer. Okay. You want to grow tomatoes. So what you do is you start off with a certain amount of money. You go to the seed store. You turn that money into seeds. So for any particular amount of money, the store will sell you a number of seeds. That's a function. And then, reliably, you grow. All right, I'll call this store. Grow. And then you grow tomatoes, and each of those seeds might give you a certain number of tomatoes. And so you get some number of tomatoes. Okay? So we can think of this whole procedure in terms of two different functions. The number of seeds per certain amount of dollar, and the number of tomatoes per certain amount of seeds. However, as a farmer, you're not actually interested in there being two functions. What you want to know is how many tomatoes you'll get starting with any particular dollar. And actually, one of the reasons we introduce functions in terms of these arrow notations is it makes explaining what we want to get, what new function we want to build out of these two, really easy. Because all I want to do is I want to take these two diagrams and overlap them. Come on. Yeah? This will give me a new diagram, starting with this dollar, that. 1, 2, 3, 4, 5. Tomatoes, 60, 80, 100, 130, 290. This particular function has a name. It's called a composite function. We use a specific notation for composite functions. The order is you start with some input, you evaluate f of x. Okay? You evaluate f, the result of that function, the first function, and then you plug this value in to another function, g of x. So the resulting function, the resulting composite function, we call it this, hold on. We call it g of f, or g of f of x. Sometimes I refer to this one as the inner function, and sometimes I call this one the outer function, to denote where they are in the relationship. And the idea here is, in terms of what order I'm going to evaluate, starting with this, you evaluate the inner function, and then you evaluate the outer function. And that gives you the overall composite function. Okay? So I'm going to use this notation to describe the relationship between these functions, how I put them together. We'll do a couple exercises. I hope it'll make a little bit more sense to you. But the result here is that I can then use this new function and say, hey, if I start out with $3, how many tomatoes will that give me? And you can either go 3 becomes 100, so 100 tomatoes, or you can go back to your original diagram. It goes $3 gets me 60 seeds, 60 seeds gets me 100 tomatoes. Okay? So that's the basics behind composite functions. We're putting one function inside of another function, kind of. Figuratively, but in reality what we're doing is we're evaluating one function and then using the output of one function to evaluate a second function. Okay, so here is a fun exercise. Let's try this ourselves. The deal is I am a hotel owner. And there's a party, and the party's full of dogs, and all the rooms in the hotels have partying dogs in them. And so I'm going to chase the dogs out into the courtyard, and the number of rooms I empty determines how many dogs there are in the courtyard. Okay, so this function tells me how many rooms I empty. If I empty 3 rooms, it says I'll end up with 10 dogs in the courtyard. Does that make sense? So it tells me, you know, how many dogs I'm going to end up. And then I go and look up on the internet. I have a list here. Essentially, if I have this many dogs in a courtyard, it's going to be this loud. If I have this many dogs in the courtyard, it's going to be that loud. Okay, so it's another function. And what I want to know, because I don't want the cops to come because it's too loud, is the relationships between how many rooms I empty. The input is the number of rooms I'm going to empty into the courtyard, with how loud it's going to be. The cops don't care about the dogs, they care about how loud it is, right? So how do I make a relationship between, how do I plot out this function? Oh no! How do I plot a function g of f of x? Which is, g is the number of decibels as a function of the number of rooms I empty. Let's start by evaluating this for a few. So you can go g of f of 1. Okay. When x is equal to 1, the number of dogs I get is 4. And then I can evaluate for 4 dogs, that corresponds to 40 decibels. So for one room, you get 40 decibels. One room, 40 decibels. And what we're going to do is we're going to repeat this for a bunch of them. I'm going to do the next one, and then you can do the last 2. If I empty 2 rooms into the courtyard, so g of f of x, when x is equal to 2 rooms, I get 6 dogs in the courtyard. If there are 6 dogs in the courtyard, that means there are 60 decibels. So empty 2 rooms, you get 60 decibels. Try it for the last 2, and then I'll show you how to do it. I'm going to erase these. So when I empty 3 rooms, the number of dogs is 10. And then you look up 10 on this graph. When I have 10 dogs, that corresponds to 100 decibels. When x is equal to 4, oh, the last one actually didn't have any dogs in it. So you still get 10 dogs, and then g of 10 is equal to 100. So both of these go to the same number. Okay? And so this is the function, this arrow diagram plots out the function g of f of x. Okay? So one issue that people go through is there a difference between f of g of x and g of f of x? I mean, yeah, in terms of this there is. Like, if you choose the number of dogs, that gives you a certain number of decibels, and then you can't go from decimals to, like, how do you, there's no other, So in terms of individual specific functions, sometimes it doesn't make sense to distinguish between these 2 operations. But what I want to do is think about this whole process operationally, which is to say, you look up one and then you look up another, okay? So this expression corresponds to 2 different ways of combining tables, 2 different orders of looking things up. So here I've got us, and you get different values if you do it in different orders. So here I've written out 2 more tables, and let's fill in these functions. Okay. So x can be 1, 2, 3, 4, and 5. All right. So how do I fill this in? This one is f of g of x. So first I'm going to evaluate g of x and then plug that into f. So when x is equal to 1, g is equal to 1. When g is equal to 1 is the input here, f is equal to 4. Okay? Let me try the next one. When x is equal to 2, that corresponds to g is equal to 2. When g is equal to 2, when the input, so you input this into there. When the input's 2, the output's equal to 1. Try the next one. When x is equal to 3, the output is equal to 2. When you input 2 into the f function, you get 1 out. When x equals 4, the g of function, the output is 3, and then I'm going to plug 3 into this function. Output is equal to 3. Last one, 5 is equal to 1. That corresponds to 4. So the result is a table. What does this table mean? I don't know. It depends on the context. But in essence, this is a relationship between the inputs of this table and the outputs of this table. Okay? These relationships are a little bit easier. They make a little bit more sense if you're drawing them in terms of like those pickle diagrams. But life's not always about pickle diagrams. Sometimes you need to write them out as tables, and I'd like you to be able to do this as an activity. So try yourself filling out the last table. Do it the opposite way. Which order are you inputting and outputting? In this table here, this is g of f of x. And that means that you evaluate f of x first and you plug that into g of x. In other words, this equation relates the inputs in this table to the outputs in this table. Okay? How do we do that? When x is equal to 1, f is equal to 4. Input that in here. 4, output 3. When x is equal to 2, the function's output is 1. Then you look up 1 in this table. 1, output 1. Oh no. When x is equal to 3, the output's 3, and then you look up 3 on this table, and its output is 2. Next one, 4, 1, 1, 1. 4, 1, and then you look up 1 in this table. 1, 1. And the last one, 5. The output is 2. Output is 2. Okay, so in the last activity, the one just before this, I was saying that there's a difference between this function and this function. What's the difference between them? Well, let's just focus on there being a difference between them. This one, this is the list of outputs for all the inputs, and this one, these outputs for the inputs. And you see that these columns don't match. They're different functions. You get different functions in this way. So it's important to know operationally what I mean when I say make a composite function. It's not as tricky as you'd think, and when we do it algebraically, it's actually fairly straightforward. It's a lot less of this looking up weird things in tables, but it's still a helpful thing to know about. Okay, last step. Let's talk about domains and ranges for this. So how do I figure out the domains and ranges? The easiest way to talk about this might just be to fill out the table. But when I'm filling out this x column, do I use this one or do I use this one? Well, what does this mean? Oh, geez. What does this mean? It means first I'm going to evaluate f of x, and then I'm going to plug that answer into g of x. Okay? So first I'm going to evaluate f of x, and then plug it into g of x, and that means that this is the overall input. And then... Wait, what happened to that column? Did I forget to write the column in? I didn't fill in this column. Okay, give me a second here. 4, 6, 2, 1, 0, 2, 11, 2, 8. All right. Sorry about that. So like I was saying, it's the overall input of this column is going to be the input of this function, the inner one. Okay. So if you want to, you can copy that out. 1, 2, 3, 4, 5, 6. So for each of these values, there's going to be an output. Let's figure out what they are. When x is equal to 1, the function f's output is 2, which leads down here. plug 2 into the g function, and you get 6 out. So that's 6. For x equals 2, the output of that function is 0, and then I go to plug it into this function. 0 isn't one of the entries. So 0 is not in the range of the g function. It's not in the domain of the g function. And so the output does not exist. Okay? Let's go to the next one. Input 3, output 3, plug 3 in here, look at the 3 column, output 2. Just right. Input 4, output 1, you look up 1 in this table and you get 4. Input 5, the output's 4, you look up 4 on this table and the output is 1. Input 6, output 5, you look up 5 in this table, output 0. Okay? So we have to exclude x is equal to 2 from the domain of this function. Domain of g of f of x are the numbers, 1, 3, 4, 5, and 6. Okay. Wait, hold on. Yeah. So the domain of g of f of x, that composite function, is the domain of f of x but we remove from it the values x where f of x is outside the domain of g of x. In other words, because when x was equal to 2, the output of f is 0, and 0 isn't in the domain of the g function, x equals 2 can't be in the domain of our composite function. Okay, so that was a lot of ideas, but the ideas really aren't, they're not that complicated. Composite functions are a little bit weird, but you're going to have to get used to them because you're going to see a lot of them in the future. Here's our medicine wheel. We have division, addition, subtraction, multiplication, and composition. Okay? So the deal here is if you add two functions together, you can do it, or subtract two functions. You just do it by subtracting their outputs. Just make a new table, subtracting or adding their outputs. Same thing with multiplying. All right, so that is add their outputs, or you can subtract them. That function is defined by subtracting their outputs for any particular input. There's multiplication, where you just multiply their inputs together. Division was a little bit more complicated. You divide them except if g of x is equal to 0. So you have to be careful not to let the output of the g function be 0. So division deserves its own plot on this. And then there was composite functions, which is when I put the output of one function into another one. Okay? And you have to be careful with composite functions, like I said, but that's the basic concept. When we do these things in terms of algebra, hopefully it'll make a little bit more sense. Okay, I'll talk to you later. Bye-bye.